Alright guys, it's Miss Summers with a set of notes for my friends who are either at home or maybe you just wanted to hear these sets of notes twice about origins of the universe. So we just finished up our intro unit on kind of the basis of science and all that fun shenanigans. So now we're going to get into the real nitty-gritty of material, and what better way to start than with space. So today we're looking at the origins of the universe. We want to know how we know that the universe got to where it was, like what evidence do we have of that, all that fun shenanigans. Looking at the origins of the universe as well as origins of solar systems and how we organize everything, how we all fit into this big thing that we call the universe. So we're going to clarify something, and I know I've gotten on this soapbox before, but I'm gonna get on it again because it matters. It is the word theory in science. Okay, a lot of times I hear youngins, they'll be like, well, that's just a theory, Miss Summer, so it's not like proven, right? It's just a theory. It's just like a guess, somebody's like best idea, but like they don't have a way to prove it. And that is completely and 100% incorrect. A theory is an explanation. When we use the word theory in science, we're explaining some aspect of nature, and a theory, in order to stand the test of time, has to be repeatedly tested and verified. So it is constantly being supported by multiple pieces of evidence. All right, there's always evidence for these theories that we're going to talk about. Every time we talk about a theory, we're going to look at what can you observe that shows you that explanation happening. Okay, a theory is not a guess. A theory is a why. That's why it ends in why. A law, okay, is not something that's better than a theory. Usually when we hear a law, we think about things that are set in stone, so laws never change and all this. No. A law in science is a description of a phenomenon, okay? The nice thing about laws, the reason they're helpful, is we can use them to make a prediction, okay? So, for example, Newton's second law of motion is force equals mass times acceleration. That's all the law is, all right? So I can use that formula to say, okay, I have this kind of mass. If I apply this force, this is how much it's going to accelerate by. Again, just like scientific theory, there's repeated pieces of evidence that support it. All right, repeated successful predictions. The difference is a law just describes. It doesn't say why, it just says what. It says this is here, and that's it. All right, so a theory doesn't become a law if it's like really good. I think that's a big misconception in high school science kids, and maybe in other kids too. I don't know. But yeah, theories are not inherently inferior to laws. It's not like they're bad. They're like not good enough to be laws. Theories and laws are fundamentally different things. Okay? So the reason I bring that up is because we're going to talk about a theory today called the Big Bang Theory. That's exciting, right? So the current understanding of how the universe began is the Big Bang Theory. So again, it's a theory. It explains how the universe got to where it is right now. So the basis of this theory basically says that the universe started at a point and it expanded. Okay? Now, does this theory necessarily tell us like where this point came from or like why it started? Not necessarily. Those are still questions that we're working on. That's okay. That's how science is. All right? But the theory explains that the universe got to where it was because it's constantly expanding over billions and billions of years. All right? So how do we know that? Or what does that mean for us? The universe we live in is expanding. It is getting bigger every second of every day. Again, we need evidence for this. So how do we know the universe is expanding? We see galaxies moving apart from one another. We're going to talk about that here in a second. We're going to talk about a law that goes along with it. Remember, laws are descriptions, not explanations. And based on our evidence, what we can see, light travels at a finite speed, so we can tell how far away something is by figuring out how long it took the light to get here. So we can determine that the universe started to expand about 14 billion years ago. Right? So let's talk about that galaxy evidence. All right, so how do we know the galaxies are moving apart? Because it's kind of hard to see galaxies. They're super far away. So how do we exactly tell that they're moving away? What we're using is the Doppler effect. We're looking at the light that's coming from the galaxies, and it's either going to be red-shifted or blue-shifted. So let's look at the Doppler effect. The Doppler effect happens when you have a change in a wavelength from a source because that source is moving. Okay, so we often experience this in the form of sound on Earth. Like if you are on the street and the ambulance passes you by, or the fire truck, or the police car, or whatever. Okay, as it gets closer to you, this sound waves that it's producing get squished together, and that creates a higher pitch. So we hear that as like a more whiny sound. And then as that ambulance drives away from you, the sound waves start to spread out. And we hear that as a lower pitch or a deeper sound. Okay? In light, obviously we wouldn't say high pitched or low pitched for light. We would look at the color of the light. Light that is being stretched out shifts to the red end of the visible light spectrum. Okay? When light gets squished together, okay, if it were moving towards us, the wavelengths would get shorter and the light would be blue shifted towards the blue end of the spectrum. Well, when we look at galaxies, all the light is shifted to the red end of the spectrum. And it's called redshift for that reason. So that's how we figure out, oh, these galaxies are moving away, not towards us. If they were moving towards us, it'd be the opposite. It would be blue shift. All right. Now, I said I was going to mention a law. Right? Do galaxies expand evenly? Okay, does it matter where a galaxy starts in relation to us? Does that make a difference? All right. Galaxies do not expand evenly. So this astronomer back in the 30s, I believe 20s or 30s, a guy named Edwin Hubble, noticed that galaxies that were already far away from Earth, like they were already farther away, seemed to be moving away faster. And galaxies that are close by, they're still moving away, but they're not moving quite as fast. All right, so the farther away a galaxy is from Earth, the faster its rate of expansion. This is Hubble's law. Note, it does not tell you why the galaxies are moving faster if they're farther away. It just says they will. And there's a mathematical formula that goes with all this. I don't expect you to memorize that. If you wanted to, go for it. But yeah, that's what I want you to know about Hubble's law. Galaxies that are far away move away faster. Fun. Oh, look, here's a graph that goes with. Oh, we love graphs. Graphs are fun. So we have our graph. Distance is our independent variable. It's down here on the x-axis. This is actually, the unit we're using is parsec. That's like a super great big distance. So you might be like, Miss Summers, I thought parsecs were a unit of time. That's what Han Solo told me in Star Wars. Sorry, he lied to you. That's okay. It's okay. All right. But basically, we can see this relationship. The farther away a galaxy is, like over here, like 2 times 10, I think that's raised to the 6th parsec. All right. That is expanding, or that is moving away at a rate of like 900 kilometers per second, which is super fast, by the way. Velocity, how fast the galaxy is moving away, is my dependent variable. Look at us reviewing some graphs. Yay! Fantastic. All right. So that's what I want you to know about the universe. It's getting bigger. Things that are farther away from us are moving away faster. Okay? So let's talk about the solar system. All right, we live in a solar system that's heliocentric. We talked about that word. Just means sun-centered. All right, so we want to know, how did we get to be in this sun-centered little solar system? And the answer to that is nebular theory. This explains how star systems are formed. Okay? It also explains the formation of planets and galaxies in general. So basically what it says is that you have these things called nebulae, which are basically great big clouds of dust and gas, mostly hydrogen. And these nebulae start to rotate. They will start to spin. Okay, maybe it's because something passed by them, like an asteroid or a meteor or some other galaxy. Something passed by them and it begins to rotate this whole mess. I like how I'm using hand motions even though you can't see me. Just pretend my hands are rotating. All right, as they rotate, everything gets sucked to the middle due to gravity. Gravity pulls things to the center. And you get this flat disc. You can think of it like this guy tossing this pizza crust, all right? The reason they do this is to get everything to flatten out, all right? They start with like a ball of pizza dough, and obviously that wouldn't make a good pizza, so they rotate it to get it flat. Kind of the same idea. All right, so again, this is a theory. We have to have evidence. We have to be able to observe what this is saying. So how we do that? We're looking at the Hubble telescope. The Hubble telescope is a deep space telescope, so it's looking into galaxies like super duper far away. And we can see young stars forming in nebulae. Now you might be saying, Miss Summers, how do you tell how old a star is? Like, how do you do that? You look at what the star is made of based on the kind of light that it's producing. We can figure out how much helium is in the star versus how much hydrogen, etc. Planets orbit on the same plane around the sun, which means Mercury and Venus and Earth and Mars and Jupiter, Saturn, Uranus, Neptune, all those thingies, even like the asteroid belt, your minor planets, your dwarf planets like Pluto, all right, they all are moving the same way around the sun. We all make the same motion, okay? So it's not like some willy-nilly like Earth is going that way and Mars is going the opposite direction or whatever. We're all on the same plane. Most planets also rotate in the same direction, okay? So on Earth, the sun rises in the west and sets in the east because of our rotation, because of the direction we're rotating. If you went to Jupiter, it would be the exact same. The sun would rise in the east and set in the west. On Neptune, it would be the exact same. It would be really hard to see because the sun's really far away from Neptune. All right, but you get my point. The exception is Venus, and I do like talking about this because it's kind of fun. So the question is, why does Venus rotate backwards? Why does it not go the right way? The hypothesis, the best explanation or the best guess that we have, remember, a hypothesis is what we think the answer is. The best hypothesis we have for why Venus spins backwards is because early on, something really big, like maybe the size of a planet or like a giant asteroid, came into our solar system and ran into Venus and just boop, slapped it. All right, and that force caused this rotation to go backwards. All right, which kind of makes sense because Venus not only does it rotate the wrong way, it also rotates very slowly. A day on Venus is longer than a year is. So that's a good answer. That's a good guess. All right, just for funsies, here is an example. Here is an example of a nebula. Okay, so this is this cloud of dust. This is the exciting star, which means it's a young star. It's just started fusing, which we'll talk about what that means later. All right, we can see there's this little outline of this debris field of this stuff that's going to eventually coalesce into planets. So this will turn into its own little solar system. All right, and lastly, the last thing I'll leave you off with today is the difference between a solar system, a galaxy, and a universe. They are not interchangeable. They depend on the size, all right? The universe is the biggest thing, okay? The universe is this big umbrella that everybody lives under. Everybody lives in the same universe, all right? The universe contains individual galaxies, all right? So our galaxy is the Milky Way galaxy. The closest galaxy to us is called Andromeda, which is super fun. Each galaxy has billions, if not trillions, of solar systems. A solar system has a star in the center of it, so something like the sun, or Alpha Centauri, or any other star that you look up in the sky. And each star potentially has lots of planets. So the neat thing about this is that, we know the universe is super expansive. There's billions and trillions of galaxies, and each galaxy has billions and trillions of stars. And we don't know quite yet, like, how many planets each solar system has on average. We're not sure on that number yet because stars can be very different. All right. But what it potentially means is there's a lot out there. So we haven't discovered nearly any tiny percentage of it, which is kind of exciting. All right. You can think of the universe, the solar system, and the galaxies like these little Russian nesting dolls. All right. The universe contains the galaxies. So the galaxies are smaller than the universe. The solar systems are within galaxies. So solar systems are smaller than galaxies. Planets are within solar systems. So planets are smaller than solar systems. And so on and so forth. This would be smaller than planets. Okay? So I'm going to leave you with that. If you are at home, I need you to go ahead and get started on that Big Bang assignment. All right? It's going to help reinforce some of the stuff from this notes. And we also have some data analysis about Hubble's law. All right, so I want you to go ahead and take a look at that. If you have any questions, y'all just let me know.